topic is on quantum thermodynamics, and I relate it to the end of the universe, how the world will end. The history of thermodynamics. As a science, thermodynamics was formulated in the 18th and 19th centuries. At that time, it concentrated on investigating the transformation of different forms of energy. Thermodynamics was then formulated as a science about temperature, heat, and also interconvertibility of heat and work into each other. So this guy, the history of thermodynamics started with G. Galilei, which was born in 1597, who introduced the concept of temperature and invented one of the first thermometers, which now looks like this. It was G. Black who was the first to use the term thermodynamics, and in 1772, G. Bell introduced the unit of measuring the amount of heat, the calorie, which was it was W. Thomson who introduced the term thermodynamics to conventional use. And two types of thermodynamics. In the 20th century, thermodynamics become basic independent division of theoretical physics, dealing with the study of general properties of physical systems under equilibrium, as well as common regularities taking place while attaining equilibrium. Thermodynamics is divided into phenomenological and statistical thermodynamics. So the first class of thermodynamics proceeds from experimentally established principles and operates with the recognized data on properties of physical bodies. And the second one is statistical thermodynamics, which is based on representations of molecule or atomic structure of physical bodies. Its tools are statistical methods and mathematical apparatus of probability theory. So my topic is about thermodynamics, and I want you to all review something about energy. So thermal energy is the part of the total potential energy and kinetic energy of an object or sample of matter that results in system temperature. It is represented by a variable Q and can be measured in joules. So in this picture, you can see that imagine that the ball is moving this towards us, and the car has motion. In this picture, we can see the kinetic energy carried by the ball in the car, and elastic potential energy carried by the string, which is called vibrator. And in this picture, we can see that the gravity, which is gravity potential energy. At the highest height, the bigger GE that an object will carry. Some important things to know about energy. Energy flows backwards in time in exactly the same way as it does forwards in time. There's no way to know that a video is being played in reverse. Laws of film editing is even with time flowing backwards, laws of physics are being obeyed. So basically, if you imagine that the car goes through, like my left hand would be a car, and it's going through a string, which carries, which transfer kinetic energy into elastic pressure energy. It would be like something like this. So the car goes in, pushes back the string, and the string will push the car backwards. And if you play it backwards, it will be exactly the same. If the car goes in and then pushes back, see how no matter if you play it forwards or backwards, the video will look the same because the physics laws obeys. If you reverse the direction of the particles and then follow the laws of physics, you will get the exact same results in reverse order. Even for chemical and nuclear reactions, the laws of physics works the same backwards and forwards. And now you may ask that, well then why the universe didn't go back to its beginning when the Big Bang happened? There's only one reason that these events never happened. It's because of the second law of thermodynamics. And the first concept that you need to understand is called entropy. So I did a lot of research, and it's kind of complicated. So I make it simple for us, for you guys to understand. So let's say that on the left side of the basket, you have an apple, a banana, an orange, a watermelon, and a grape. And on the right side of the basket, you have nothing. If you want to make it 4 against 1, there's only 5 ways that you can do it. You either move the apple, banana, orange, or etc. And then if you want to make it 3 to 2, there's many more different ways to do it. And imagine particles are moving without any color in this small little area. Once you release or remove the wall, particles will start flying and will go over the wall and fulfill the whole box. But then they will never gather together back in the small space against you without any counterforce. So they will just flying randomly in the box without going together. So the definition of entropy. But there are more ways that something can happen. Physicists give this a name, and we call it a higher entropy. And the 4 to 1 group has a lower entropy, and the 3 to 2 groups has a higher entropy. Which is basically, you can just say, it's basically like explaining complexity. When something is more complicated, when there's more ways to do something, it has a higher entropy. What about now? What about 500 to 0? Equal to now. The more evenly the balls are spread out between the two spheres, the higher the entropy. Eventually, it will be like 250 balls against 250 balls evenly. And at this point, there will be exchange, but they will stay at 250 against 250. You won't be like random changes for like 200 to 0. So if the balls go back to its original position, it means that the entropy has decreased, which is violating against the second rule of thermodynamics. Therefore, you will never. Keep in mind that entropy also applies to energy. This is a picture. As you can see, the temperature 2 carries higher energy, so it's warmer than temperature 1. And eventually, these two temperatures. This is why, because the heat flows from higher temperatures, lower temperatures to make them balance. And this is just quantum mechanics. Because the entropy on both sides will be even, and at that point they won't change. Because of what we just learned about entropy. The entropy is highest when the energy has spread out evenly throughout all particles. The example about 500 watts. This is why heat flows from warmer objects to colder objects until they reach the same temperature. So how we normally do, how we normally put machines and engines to work is, there's your resources, fire, which would, step 1, the heat or the entropy will become evenly so that the particle in that little box will carry the energy in order to push. The balls will push against the wall and stay, causing useful work to be done. But then, once it's reached its entropy, which is evenly in temperature or energy, there's no more work that can be done from particles. Then we need to move for energy. In order to look for more energy, we need to move the box to ice, so that temperature will flow from the box into the ice, which makes the ice melt. And then you will be able to do the same step from step 1 again to keep it over. Eventually, the ice will melt and the fire will die out, and all engines and life forms need to dissipate heat to a colder object in order to keep operating. However, all objects will eventually reach the same temperature if we wait long enough. When everything reaches the same temperature, no engine or life form will be able to continue operating. And that's how the world will end. So shall we try to violate the second law of thermodynamics so that heat will flow from a colder object into a warmer object? And here's a video to show where you're going to do this.
Suppose we use this to try to violate the second law of thermodynamics by causing heat to flow from a colder object into a warmer object.
So everything from here will be like reversed from common sense.
Energy is transferred from the balls to the spring, causing the box's temperature to become colder than the ice. Now heat flows from the ice to the box because the box is colder than the ice. Suppose we now compress the balls together, causing the box's temperature to become hotter than the fire. Now heat flows from the box to the fire because the box is warmer than the fire. This is how refrigeration and air conditioning work. The ice is getting colder and heat is flowing from the ice to the fire. However, the addition of energy increases entropy, and the second law of thermodynamics is therefore not violated. All refrigeration and air conditioning requires the addition of energy. Machine by using an engine to power this refrigerator, and using this refrigerator to cool the engine. Refrigerator will always require more energy to cool the engine than the engine can supply. The energy that we dissipate as heat cannot be used again to do useful work, and the fire will eventually run out of energy. We can keep the fire burning by adding fuel, such as coal or oil. Oil in the earth, and we will eventually run out. We can keep the fire burning by using nuclear energy. Nuclear reactions. The earth also has a limited supply of elements useful for nuclear reactions. When we run out of nuclear fuel on Earth, we can keep our engines running by using solar energy from the sun. For millions of years, it too has a limited amount of fuel and will eventually run out of energy.
And so basically that's just the thermodynamic way of looking